Thank you very much. Does that work? Wonderful. Good. First of all, I need to clarify that I'm not the person who discovered Scholz's star. At this point, all credit goes to Ralf-Dieter Scholz, my colleague who's in Potsdam. There are two persons with the same name in this field. And second, I need to give all credit for this title of the talk to Scott Volk, whose thesis is titled Watching Stars Go Round and Round, and John Lennon, whose talk is titled Watching the Wheels Go Round and Round. So I'm going to talk about brown dwarf rotation in the next 10 minutes. So this is all brand new work, and if you look in the abstract, you're going to see I'm going to say things that are different from what is in the abstract, just to illustrate how fast it is moving forward. I want to highlight the contributions of two of my collaborators, Dawn Peterson, who's in the audience today, and Kevin Moore, who is about to start his PhD at McGill. Those two have done a lot of the core work for this project. Right, now I need to go forward. How does that work? Right. Given the sometimes extreme temperatures we had to endure, I think it makes sense to start with polar exploration for a little bit. In 1911, Amundsen and Scott reached the South Pole after years of struggle, right? Immense sacrifices. And if they would have just waited 50 years, they could have done exactly the same thing, much easier, faster, with a helicopter, which you can see here in the background, right? Why am I telling you this? Well, in 2004, I finished my PhD after immense struggle over years, not quite reaching the South Pole, but almost. And I was trying to scrape together rotation periods for very low mass stars and brown dwarfs. If I would have just waited 10 years, I could have done the same thing much faster and more efficient and better with the help of K2. And these two plots just illustrate a little bit the progress that has been made since then. So these are rotation periods for the Pleiades in 2004, and those at the bottom, at the left side, are the M-dwarfs periods that we had at the time, about a dozen. And on the right-hand side, you see a figure from Rebold where what we have today. We have hundreds of periods for M-dwarfs. This plot, by the way, on the left-hand side was presented at Cool Stars 2004 in Hamburg, which was my first big meeting. For this progress, all credit goes to the Kepler and K2 science teams. Thanks to them for making that possible. And this allows us to revisit the problem of brown dwarf formation, brown dwarf rotation. I'm going to focus on periods here because that's my method of choice. By now, we have something like a period database for brown dwarfs. I wouldn't have dared to use that word 5-10 years ago. And on this figure, you see sort of the growth of the number of periods over time, a huge jump 2009 with the monitoring campaigns in the ONC with the ESO Wildfield Imager, fantastic instrument for this kind of work, and then another jump with K2. So this is still not a huge sample, it's close to 300, particularly not if you split it up in age groups, but it's getting there, right? This is a solid sample to work with. Right, we've known for a long time that brown dwarfs are fast rotators. This goes back to VSNI measurements from the 90s. The questions today is, how fast are they rotating as a function of age? Can we track the spin down, if there is any spin down, and why? What's going on there? And if you're interested in the stellar rotational evolution, brown dwarfs give you sort of a chance to check your model's predictions in a very extreme parameter domain. After this meeting, I'm not sure anymore we understand the spin down of solar mass stars, so this is an extreme case of where we can try out things. Right, so this is the big overview. This is the rotation evolution period versus age, and this is a plot I've made for the Protostars and Planets review in 2014. You see that young brown dwarfs, ages of a few million years, rotate with periods of a couple of days, typically, with a wide spread. If you go to old brown dwarfs, you get periods of a few hours, again with significant spread. And if you're thinking about the typical mechanisms that control angular momentum loss, then at the young stages, you would try to talk about the disks. What impact has the disk on the rotation? And on the old objects, the question is there any wind in brown dwarf that carries away angular momentum? Now, there's one important lesson to be learned from this diagram, which is prior to K2. If you try to link these two domains, old and young, you find that while old brown dwarfs rotate fast, they are not quite as fast as you would expect from angular momentum conservation, which is the dashed line here. So you probably need to introduce a little bit of rotational braking to reproduce the rotation rates in the old objects, but it's not much, right? So if there's any wind braking, it's very, very weak or only over a short period of time. That's the first take-home message. There are 3 take-home messages in this talk. Right, I'm going to focus on young ones, young brown dwarfs now, because that's where we have made the progress over the last few years with the clusters that have been observed with K2. And here the question is about the disks. What impact has the disk on the rotation? So those 2 plots that I'm going to show you here, those are figures I wanted to have for a long time, and they only become possible with periods from K2 in combination with infrared access from Spitzer or WISE. That combination is very powerful to probe what impact the presence of a disk has on the rotation. So those 2 plots show exactly the same thing, infrared access on the y-axis versus period, and they fortunately give you the same answer. The objects with disks, which are on the upper halves of these diagrams, are predominantly or almost exclusively slow rotators. Right? They're on the right-hand side of that diagram. This is still a small sample, but it's not a statistical fluke anymore. This is solid, and we need to take this seriously. Brown dwarfs with disk rotate on average 50% faster than brown dwarfs without. So there are a few objects where you can see the link between the disk and the object more directly than this here, and those are the dippers. There are a number of posters here about dippers in stars. Dippers are objects where we think there's a warp at the inner edge of the disk caused by magnetospheric accretion, material falling in, and that warp is rotating and eclipsing the objects occasionally. We see the same thing in brown dwarfs. So this is an example here, K2 light curve for brown dwarf and Upper Scorpius, where you have these regular recurring dips with the same period as the rotation period of the brown dwarf. So that tells you there's a direct link. The warp at the inner edge of the disk, where the accretion funnel begins, rotates at the same rate as the brown dwarf. This is sort of a smoking gun for disk braking. And the third way to look at this problem is to go back to period versus age. So this is a plot with lots of dots. Each dot is a period, and on the x-axis you have age. This combines ground-based data from various sources and K2 data in Taurus and Upper Scorpius. And green overplotted are sort of typical values, just to guide your eye a little bit, median and upper and lower limit. And you see immediately one thing, the periods in Upper Scorpius, here on the right-hand side, the oldest ones, sit lower. They are faster rotating than in the youngest regions, in the Ionian Sea and in Taurus. That's good because they spin up, and therefore you expect that they contract, and therefore you expect that they spin up. But again, they are not quite as fast rotating as you would expect from angular momentum conservation. You need to introduce some level of rotational braking to reproduce that trend. And one way of doing that is just to keep them constant for a while and then start the spin up. That's what I've sort of indicated here as a toy model, but there are other ways of parameterizing that. But there needs to be some level of rotational braking at these early ages. So we have 3 different pieces of evidence, all saying the same things, fortunately. There is rotational braking that is mediated in some way by the presence of the disk in brown dwarfs. And all of this is going to be published in a paper that we've just submitted. Lead author is Kevin Moore, and I'm pretty sure one of you is going to be the referee. I'm looking forward to seeing the email. Right. So this still hasn't answered the question that I've posed at the beginning. Why are brown dwarfs fast rotators? And I think a fair guess is to say they are fast rotators from the beginning. Initial conditions is the most important parameter here. So it makes sense to think about rotation in terms of formation scenarios, right? A few years back, I learned from Ignace Snellen that the solar system planets, at least those that are not tidally affected, obey a spin-mass relation, a power law between the rotational velocity, rotational velocity and planet mass. And Beta Pig b, the first exoplanet with a measured spin rate, fits into the diagram as well. So it's worth asking, where are brown dwarfs in this figure, right? Can we put them there? These are all objects that are not expected to experience any rotational braking. So this is almost certainly an imprint of initial conditions. So to put brown dwarfs in this figure, I took the periods from the youngest ones where there wasn't enough time yet to break down and evolved them forward to the age of the solar system, assuming angular momentum conservation. If you do that, you get this. So that's a figure. You can stare at this for a long time. The orange dots are the brown dwarfs, the blue ones are planets, and the brown dwarfs sit right on top of the relation of the power law. They just extend this for another order of magnitude in mass. Right. What does that mean? I don't know. I can't give you the full answer what that means. But there's one thing to be learned from this. If this is really an imprint of initial conditions, it means that these brown dwarfs, when you catch them at when they're youngest, still have their primordial angular momentum. They're still sort of the primordial rotators. And that is good because it means we might be able to use rotation to learn something about the formation process, to learn something about initial conditions. So that's one thing, but I'm pretty sure there are more things to be learned from that figure. So let's go back to that for a moment. This happens to be velocity proportional to the square root of m, which is reminiscent of the breakup velocity or the escape velocity. So one way to read this diagram is this. These objects all come from different formation scenarios, right? There's a wide range of formation processes. Co-accretion here at the bottom, this is Mars. This is Earth, which sits below the line because it's slowed down by the existence of the moon. This is Uranus, Neptune, Saturn. So all these are probably forming in a slightly different way. Those objects form from disk fragmentation, and those form from core collapse, the Taurus brown dwarfs that are seen in isolation. So there's a range of formation scenarios, and they all follow the same line. What is common about these formation scenarios? It's accretion. At some point, they all gather material due to accretion. So one way to read this is while they are accreting, they at some point will spin faster and bump against that limit, and that regulates and controls the accretion ultimately. So this is one possibility here, that rotation controls ultimately the growth and the accretion of these objects. Right. Summary. Rotation in brown dwarfs is important. They're fast rotators, and that is going to affect many things in their evolution. It's driving a lot of the chromospheric activity, the cloud atmospheric activity that we've heard so much about this conference, and have ignored this topic entirely. Rotation is going to drive the activity early on when brown dwarfs are still M dwarfs. It's going to cause radius inflation, all sorts of things. And as I've shown you in this talk, it might also have an impact on the formation scenario and control the final stages of accretion. And I think I stop here. Thank you very much.
We have time for some questions. Staff?
Stan Metra of the University of Western Ontario. So brown dwarfs can rotate close to breakup even at the old ages. I was actually wondering, looking at your diagram that showed the scaling law. Yeah, so you say the scaling law goes via square root of mass, which is what you'd expect for breakup velocity scaling law. Why is the breakup velocity slope different than the scaling relationship then?
Because breakup velocity unfortunately also includes the radius. The mass radius relation matters here.
I see.
Kim Moore-Duong, Amherst College. I was wondering a little bit about what we know about the multiplicity or the binarity of the Taurus brown dwarfs and the ONC systems, and how that might be affecting their angular momentum evolution.
So that's a great question. So one reason why K2 is good is because it gives us access to samples that are already well characterized. So in Taurus in particular, we picked objects where we have lots of complementary information about disks, about accretion, but also about binarity. So all the objects in Taurus, those ones, have been observed with high angular resolution, and there's no evidence for any companion. That doesn't mean there isn't a radial velocity companion, so we have to talk to other people to find out if that's something people are interested in and finding out, but there's at least nothing down to a few AUs.
Okay, I have a question. What can this tell us about the possible presence or absence of planets around these objects, which might be taking some of the angular momentum in the system?
So yeah, that's an interesting point. If you're asking why are stars or M dwarfs rotating slower than brown dwarfs, right, at early ages already, one possible answer is that they experienced more angular momentum spread to orbital separations, right? The brown dwarfs have low binary fractions. That's at least what we know. We can't really comment yet on the planetary fraction, how many planets they have, but they have a low binary fraction, lower than solar mass stars, and that might indicate they retain the angular momentum in one object.
Okay, one more question, right there.
Ansgar Reiners from University of Göttingen. Thanks, Alex, for the nice talk. I was wondering why you were showing us the rotation rates in terms of surface velocity. At least in the solar system, I think the rotation periods are, I mean, they're not so different, but of course, surface rotation scales with radius. And I would always expect that the larger ones have higher surface velocities. Why are you thinking in surface rotation and not in periods?
You can make the same plots with periods, and you say the inversion, right? You see the same thing, it just goes in the other direction. This is for convention. People in the solar system use that, and that's, yeah. So if you can do the same thing in period. You can actually do the same thing in angular momentum. It shows another power law. No matter what parameter you're choosing here, you see that relation, that trend.
Okay, one more. Thank you very much.